Okay, so for part C, we have the limit as x approaches 4 of sine of x minus 4 over tangent of x squared minus 16. So if we attempt direct substitution, 4 minus 4 would give us 0, so we have sine of 0 in the numerator. And 4 squared would give you 16, and so you're going to get tangent of 0. So this is actually an indeterminate form of 0 over 0. So we can use L'Hopital. And honestly, I think in most cases, that's going to be sort of the standard go-to move. If you've got a limit and L'Hopital is available, as long as you're using it correctly, it is a pretty direct path to the answer in a lot of cases. So the limit as x approaches 4, the derivative of the numerator is going to be cosine of x minus 4. And the derivative of the denominator is actually going to require a chain rule. So the outside function is tan. The derivative of tan is secant squared of x squared minus 16. But then we have to multiply by the derivative of the inside function, and the derivative of x squared minus 16 is 2x. Now the strategy says we should try to do direct substitution again. So if you are able to plug in 4 here, and you feel comfortable with that, that's perfectly fine. Personally, and for myself, and I know other students, anything other than sine, cosine, or tan, they kind of get nervous or not confident in their values. So you also have the option of doing what I like to call a cleanup step. And a cleanup step is I'm going to rewrite this limit so that it is in terms of either sine, cosine, or tan. So the reciprocal identity here says, right, secant is 1 over cosine. So if I move a secant above the fraction bar into the numerator, it actually becomes a cosine. So I now have cosine of x minus 4 times cosine squared of x squared minus 16, and then that simply leaves my 2x in the denominator. So if we attempt direct substitution here, when we plug in 4, we're going to get cosine of 0, which is 1. When we plug 4 in here, we're going to get cosine squared of 0, which is 1. And when we plug 4 into the denominator, we're going to get 2 times 4, which is going to work out to be 1/8. So C is 1/8, and that is the answer that I would choose. For D, if you're kind of just on autopilot and you just see a limit here and you attempt direct substitution here, well, if we plug in 0 for h, you're going to get sine of pi, which is 0, minus sine of pi, which is 0, and then you're going to get a 0 in the denominator. So direct substitution makes this an indeterminate form of 0 over 0. That means we can use L'Hopital if we like. So that would make this the limit as h goes to 0. The derivative of the numerator, don't forget pi is a number, so this is the only thing that has a variable in it. So the derivative of sine is cosine of pi plus h. Sine of pi is just a number, so the derivative of this is 0. The derivative of the denominator is 1. So now if we try direct substitution again, we're simply going to get cosine of pi over 1. Cosine of pi is -1, and -1 over 1 is -1. So our answer is going to be -1. Now there's a second option for this particular limit. Some of you may or may not recognize that this is quite a famous equation. And this equation is actually the definition of the derivative of the function sine of x evaluated at pi. So our limit is really the derivative, right, of some function f of x evaluated at pi where our function f of x is sine of x. So the derivative of sine of x is cosine x. So f prime of pi is equal to cosine of pi, which is -1. So this may be the less obvious approach, but if someone recognized that that was the definition of the derivative, if you see the difference quotient, you can invoke your calculus knowledge. But if you also just treated this as a traditional limit, it would work out, and you can see either way will help you arrive at -1. I probably personally would have gone on exam, would have gone the L'Hopital route, because I would have just been in limit mode and followed the process.